In today's video, we're going to look at how carbonyl compounds react with carbon and oxygen-based nucleophiles. We'll start with ketones and how they react with a Grignard reagent. And so this is a Grignard reagent. And remember that really, we have a phenyl group with magnesium bromide. And that's going to react as if you have a C minus that breaks apart from your magnesium and bromine. And that C minus is going to attack, I'm going to use this bond here, attack the carbonyl and kick up some electrons. Which is going to give this intermediate. And then in the second step, you've got to add a source of acid, in this case, just H3O plus. And this O minus is going to attack there, kick these electrons off to give this alcohol as the final product. If you look at sodium acetylide, that's this molecule here, or this reagent, that again is going to react just like you have a C minus, and so this really breaks apart into Na plus and a C minus. And the mechanism for this looks identical to the Grignard reagent, and you wind up with the final product where I've added an acetylide, or I've made a new carbon-carbon bond here. This used to be the carbonyl carbon, which is now bound to an OH to form an alcohol. Sodium cyanide, this with HCl and an aldehyde. Now, this could be an aldehyde or a ketone. They react very similarly. Aldehydes are slightly more reactive than ketones, but other than that, the reactions are going to be the same. The first thing that happens when you mix these two reagents together is that the cyanide gets protonated. And so we have some electrons on cyanide that are going to pick up a proton from HCl and give HCN here. So that's why we need excess cyanide, because the first equivalent is getting protonated. The second equivalent, though, we've got a Cn minus in solution, is going to attack the carbonyl to give this reagent, or this intermediate, and then HCN, which I just formed, is going to protonate the O minus to give this final product, which is known as a cyanohydrin. And these cyanohydrins can be important intermediates in things like the synthesis of amino acids. Your reagents and other organometallic reagents react a little bit differently with esters and acid chlorides than they do with ketones. And so in this one, we again are using phenylmagnesium bromide, which I'm going to draw out here. And the first thing that happens, just like before, is that the Grignard reagent attacks the carbonyl carbon and kicks electrons up to oxygen to form this tetrahedral intermediate. Here, that's the same as if it was a ketone. What's different now is that we have a leaving group on this carbon. Now, OET is not the greatest leaving group, it's a negative oxygen. But in the presence of strong base, like a Grignard reagent or most other organometallic reagents, it can be a leaving group. And so the electrons on oxygen are going to kick off and kick that leaving group away to form this ketone as an intermediate. Now, this is a neutral molecule, and it looks like we could be done here. But it turns out that ketones are more reactive towards nucleophiles than esters. So rather than a second Grignard reagent attacking another ester, before that happens, another Grignard reagent is going to come in and attack the carbonyl again and form another tetrahedral intermediate. Like so. Now at this point, there's nothing else we can do with the Grignard reagent. And so I'm going to have to add my H3O plus. Which is going to protonate the alcohol. To form this. You may be wondering why you couldn't just add one equivalent of the phenylmagnesium bromide and stop at this ketone. That reaction is messy and it doesn't work well because this ketone is more reactive to a Grignard than this ester. It's very difficult. In fact, you can't really stop here. You have to keep going. And so in order to get a clean reaction, you need two equivalents of the phenylmagnesium bromide with an ester or an acyl chloride. And that is going to go all the way to this alcohol where I have added two of my R groups, whatever the R group that the Grignard reagent is adding. You cannot react an ester with a single equivalent of a Grignard reagent. I'll give a shout out to Dr. Bass, who taught me many moons ago in my sophomore organic class that esters and Grignard reagents are so nice. It happens twice. And I haven't forgotten that esters react twice with Grignard reagents since. I'll also note that esters will react well with Grignards. They react well with organolithiums and pretty well with acetylides. They do not, however, react with cyanide. Esters are unreactive towards cyanide. So aldehydes and ketones fall between anhydrides and esters in terms of their reactivity in carbonyl compounds. And so an ester is too unreactive to work with cyanide, but you could use cyanide as a nucleophile with an anhydride or a acyl chloride. That wrapped up our look at carbonyl compounds and their reactions with carbon-based nucleophiles. Now I want to transition into reactions of carbonyls with oxygen-based nucleophiles. And so the first thing we're going to look at is the formation of hemiacetals and acetals under acid catalyzed conditions. And so we've got a ketone here, and we've got an acid. Anytime you see that, the first thing you are going to do is protonate that ketone. And so we are going to generate protonated ketone. That protonated ketone makes this carbon more electrophilic. And so now I've activated that towards a nucleophile, and my methanol, which I have here, is going to come in and attack the carbonyl carbon, kick up some electrons to give this tetrahedral intermediate. Here. Some base. We started with H plus is my source of acid, and so probably whatever the conjugate or the counter ion with that H plus would come in, but I'm just going to use a generic base here. Would come in and pluck that proton off to give this compound here. This compound is known as a hemiacetal. It's got one oxygen that's forming an ether, so I've added an OMe to my ketone, and I've got one OH molecule or one OH group attached to that same carbon. We can keep going to form an acetal, and so again, this is going to be an equilibrium reaction. We've got a newly formed source of acid. That's going to protonate my alcohol to form this. That protonated alcohol is a good leaving group. I'm going to kick some electrons down and kick off water. Form this cation intermediate, which is reactive towards nucleophiles. I'm going to bring in another molecule of methanol and attack the carbonyl carbon. Here, which can again be deprotonated by some base. To give this as the final product, and this guy is an acetal, where instead of just one OMe, I have two ether functionalities in the same place that I previously had a carbonyl compound. So this hemiacetal comes from it, half of it being the ether, and the other half I've still got an OH. The full acetal, I have replaced everything with two ether-like functionalities. If I were to use water as the nucleophile, the mechanism would look the exact same, but instead I would get this guy, and this guy is a hydrate. Is the final product. Notice that in both of these reactions, they're entirely equilibriums. And so if you want to push the reactions towards the products, you have to add a whole lot of excess nucleophile. So in the case of acetal formation, you would want to use excess methanol to push the reactant or push the reaction towards the products. In the case of trying to form a hydrate, you would want to use excess water to try and push the reaction towards the hydrate. Acetals show up in a couple of important places in organic chemistry, the first of which is protecting groups. And so cyclic acetals can be used as protecting groups. The reason we use cyclic acetals is because the acetal is favored at equilibrium when you use a cyclic acetal. Now, if we look at this reaction here, I've got a diol, which I can use to make a cyclic acetal, and we'll see that in a second. And importantly, I have two different carbonyls. I have a ketone and I have an ester. Ketones are more reactive towards nucleophiles than esters. And so this acetal will preferentially react with the ketone over the ester. And so we'll start by protonating the ketone. And then one of the oxygens on this ethylene diol is going to attack here and give this guy. I'm not going to go through the whole mechanism again. Suffice to say that if we, over multiple steps, this reaction goes on to form a cyclic acetal that looks like this. Here. What this can be used for now is this acetal is unreactive towards reductive reagents like lithium aluminum hydride, whereas the ketone was reactive. So if I now treat this molecule with lithium aluminum hydride, followed by water, or H3O+, lithium aluminum hydride will reduce esters to alcohols. So I get an alcohol, and I still have this acetal, which can be hydrolyzed using a strong acid like HCl and excess water um, to go back to the ketone. And so what this does is allow us to, in 3 steps, reduce an ester to an alcohol while not touching the ketone. Whereas if I tried to use LAH directly, I would have reduced both the ketone and the ester at the same time. Another common place that acetals, or really hemiacetals, show up in chemistry is carbohydrate chemistry. So right here we have the molecule D-glucose in its linear form. And under acidic conditions, this molecule will cyclize. If you remember, 6-membered rings have the lowest ring strain, and so glucose will form a 6-membered ring by doing a nucleophilic attack of the aldehyde here with one of the alcohols. The trick is finding which alcohol is going to be reactive towards that aldehyde. And I want to form a 6-membered ring. So the first atom in that ring is the carbonyl carbon. And as I go down the ring, I get 2, 3, 4, 5. And then if I use this oxygen as the nucleophile, that would give me a 6-membered ring. And so this oxygen is going to swing around and attack that carbonyl, but only after it's been protonated with our acid catalyst. So I'm going to go ahead and draw in a proton. So the very first step is protonating the aldehyde, and then this oxygen swings around and attacks and forms a 6-membered ring that's going to look like this. We're going to draw this in a chair conformation. Here, we've got OH coming up there. So we form the cyclic form of D-glucose like this. And so if I look at my numbers again, the carbon 1 is here, carbon 2, 3, 4, 5, and this is the nucleophilic oxygen 6. And so these stereocenters that I'm circling in yellow here are set from D-glucose. They are here, 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 and here. Those stereocenters are the same as they are in the linear form. However, we formed a new stereocenter here. And so I get a mixture of this molecule and this molecule in this cyclization reaction. Where I have changed the stereocenter of this alpha carbon here. And so this ends up being alpha D-glucose. And this is beta D-glucose, both of which are naturally occurring and have different roles in carbohydrate chemistry. I think that's going to wrap up our discussion of carbonyls with oxygen and carbon-based nucleophiles. We will pick up with carbonyls and nitrogen nucleophiles next time.